Hi, welcome to lesson 7.4, the primary trigonometric ratios. The goal of today's lesson is to determine the values of the sine, cosine, and tangent ratios for a specific acute angle in a right triangle. The reason why we want to do this is so that we can use the relationship between angles and sides of acute right angle triangles in order to solve problems. So what we're going to do is take a look at the triangle that's drawn down below here. This is mirroring the Investigate the Math from the textbook. And we want to see if there's a connection between the ratios of sides in the same triangle for similar triangles. And we want to see, of course, then how are the ratios of sides in similar triangles related. So key terms we need to know. Opposite side, that's the side that is directly across from the specific acute angle in a right triangle. So in this case that I'm showing you here, if we're looking at this specific angle here of 31 degrees, the opposite side is the side across the triangle. So side AD is the side opposite angle 31, or angle C. And the adjacent side is the side that is part of an acute angle in the right triangle, but not the hypotenuse. Or adjacent being the word beside. Adjacent side is beside the angle, and it's part of the two sides that form this angle, but of course not the hypotenuse, which is of course this side across from the right angles. And I'll just draw those in. Okay, so there's a few ratios that we took a look at here. We see that the hypotenuse for one of the triangles is AC, and that's 12.17 centimeters long. The hypotenuse for the similar triangle is BC, which is 8.51 centimeters long. And then the sides adjacent to angle C for the primary triangle ADC. DC is the side adjacent, 10.44 centimeters, and EC is the side adjacent to this angle 31 degrees, or angle C, for triangle BEC, which is 7.3 centimeters long. And then the opposite side, AD, 6.26, and BE is 4.38. Now we'll take a look at a few ratios, and ratios can be also shown in the form of fractions. So if we're taking a look at the ratio of the opposite side over the adjacent side, we're looking at side AD, and we're dividing by side DC. So the opposite over the adjacent is side AD divided by DC. Okay, so that's the opposite from this angle 31 over the adjacent side of 31. Now if we take a look at the ratio of the similar triangle, the opposite side is BE, and we divide that by the adjacent side EC. Notice the ratio that we get here when we divide those. So for the primary triangle ADC, the ratio of AD to DC, or opposite over adjacent, is 0.6, and the ratio of BE to EC is also 0.6. Notice that that is consistent with our definition of similar triangles, where all angles are equal and all side lengths or corresponding side lengths are proportional. Notice that we've got angle 31, that's a common angle between triangle ADC and BEC. They both have right angles, so therefore angle EBC and angle DAC also have to be equal. Therefore, since all the angles are equal, or the corresponding angles are equal, that means that the two triangles are similar. Therefore, if they're similar, side lengths would be proportional. And then if we then take a ratio of AD to DC and the ratio of BE to EC, we see that they have the same ratio because they're similar triangles. And we take a look then at the opposite over hypotenuse, a ratio of those two sides. We'll look at AD, which is the opposite, over the hypotenuse AC. And then we'll take a look at BE and the ratio with that of BC. And we see that both of those have a ratio of 0.51. And then we do the same thing for the adjacent, the length of the adjacent side and the length of the hypotenuse. DC over AC. So DC over AC, and then EC over BC. Those are, of course, the sides, adjacent and hypotenuse, the adjacent being compared with the side that's beside the angle of interest here, the reference angle of angle C. We look at the two triangles and we ask if they're similar. Well, we already kind of know that they're similar because of all the angles, all the corresponding angles are equal, and by looking at these ratios we see that all the side lengths are proportional. Therefore, definitely those two triangles are similar. Now we'll move along to describing the relationships. Well, if we see that the relationship between the opposite side and the adjacent side, we see that those are proportional. Same thing for the opposite and the hypotenuse, as I've already mentioned, and the adjacent over hypotenuse. That corresponding side lengths are proportional with each other. So that could be what you could write in here. Would the relationships change if the measure of angle C changed? Well, if we change this measure of angle C, then the measure of angles DAC and EBC, they will also change. The right angle would not change. And if we were to increase angle C, that would just mean that the length of AD and the length of BE would also increase. So therefore the proportionality would stay constant. Okay, so we might get a different ratio, but the relationships would stay the same. Okay. And in each of these triangles, the ratio opposite over adjacent is equivalent to the slope of AC. And we'd like to know why that may be. Okay, so the opposite side, the opposite side over the adjacent is, we're mentioning the slope of AC, and here the opposite, BE over EC, that's the slope of BC. Remember when we looked at slopes of lines in previous years, we would draw a rate triangle indicating the rise and the run for the inclination of a line. We see that the rise is the opposite, the run is the adjacent, so opposite over adjacent is the same as the rise over run. So therefore, the ratio of opposite over adjacent is equivalent to the slope. So whether it's of AC or BC, those two rate triangles would give the slope of that hypotenuse. The relationships involving the ratio of size that depend on the size of angle C. Well, again, because we're dealing with similar triangles, if the size of the angle changes, then of course the lengths of these sides will change, and also the length of the hypotenuse would change. Therefore, it's all changing proportionally according to the angle that angle C is. So the proportions will still remain constant, therefore the relationships between opposite and adjacent, opposite and hypotenuse, and the adjacent and hypotenuse, they would remain constant even if the angle is has been changed, either greater or smaller. And how could we use ratios to find angle C? Well, we could take a look at the ratios, the opposite and the adjacent, and we could do some fancy math, which we'll get to in a couple of minutes, but we could use those to find the angle if we didn't actually have angle C given to us. Okay, we'll see that in a couple minutes.